Hello, everyone. This is Huang. Today, Garima and I will present our work, DeMed, a novel and efficient decentralized learning framework for medical image classification on blockchain. The idea is that training a deep neural network requires abundant amount of data, but a single hospital may not have enough data for that. So hospitals tend to cooperate on training the model together. However, there are privacy concerns in medical data. Distributing patients' data are restricted by law, for example, HIPAA. Furthermore, some works, such as membership inference attack, have shown that it is possible to attack the model to obtain private information. Thus, we think blockchain is a perfect tool to help preserve both cooperative and private concerns. However, deep neural networks usually contains millions of weights. Storing, uploading, and downloading such gigantic parameters is extremely costly. So we think, why don't we train a simpler model? It is proven that under proper data assumptions, a well-trained self-supervised network can embed the data into features that lie in a linearly separable space. In this paper, we will apply a pre-trained MAE, mask autoencoder, a reconstruction-based self-supervised learning algorithm to help extract the features from each participant. Once the MAE pre-training is finished, the encoder will be distributed to the participants, and the participants will only need to train a linear classifier on the proposed classification task. Here, we train a single fully connected layer. This gives us two benefits. First of all, the computational cost for individuals is low, and the time needed to do one transaction is reduced. So here's our proposed framework and the comparison. On the very left, the central training is that where there's a center that has every data, and it will train the model based on the data. And so basically, the center will have data and the parameters. So, and for the second one, federated learning is that users will have their data locally, and they will train the model, and they will update the weights to the parameter center, and the parameter center will be in charge of aggregating those weights. As for swarm learning, individuals will have their own data, and it's more like a peer-to-peer. So the users will train their own model locally and interact with each other to update their weights. And as for DeMed, the users will have their own data and the distributed MAE. The users will first use the MAE to encode their data into features, and they will use this feature to train one linear layer, and they will upload the weights to the smart contract. So the smart contract will be in charge of aggregating these weights, and we think that this has two benefits. First of all, since we're uploading only the linear layer, so it's harder to be attacked. And second of all, everything happens inside a smart contract, so it makes the system safer. So here is how we are going to simulate the real-world scenario. For MAE training, we assume we can collect an abundant amount of the in-domain data without labels to perform MAE pre-training. An alternative way is to pre-train MAE on ImageNet and then fine-tune on the data we have. In our experiments, we will separate the datasets into two non-overlapped parts, one for training MAE and the other for simulating participants' data. In this preliminary work, we use fed average aggregation and assume that only a fixed number of participants will join for each weight aggregation. So in our experiments, we use two datasets. First of all, PCAM, a microscopic pathology dataset, and CopyX, a chest X-ray dataset. And Garima will continue to introduce our pipeline.
Thank you, Jen. So hello, everyone. I will be explaining the pipeline, especially the blockchain pipeline that we have used in our DeMed. So the two main components of our system are the hospital and then the multiple users who provide their weights after training on local data. And we use Ethereum blockchain and smart contracts as a communication medium. So the hospital distributes a pre-trained SSL feature encoder to the users, and it initializes a linear layer in the smart contract. What this means is that it initializes a linear model and it uploads the weights to the smart contract, as you can see in the picture over here. The users will use the encoder to extract the features of their data and train a linear model. This step happens on the local systems of all the users. A transaction in a system is equivalent to uploading the weights to the smart contract or downloading the weights from the smart contract. Weights are aggregated in the smart contract itself. So let me explain it through the diagram. Once the hospital uploads the linear layer to the smart contract, users will download these weights, and on their own systems they will use their own local data and train their own local models, and then they will upload their own weights to the smart contract parallelly, and these weights will be aggregated as per the number of users we have decided in the batch. Those users will upload their weights, and they will be aggregated. These aggregated weights become the initial weights for the next users in the batch, and we assume we have 16 users in total, and we randomly sample 2, 4, 8 online users in each round. A little bit about the implementation details and setup, blockchain and smart contract setup. So for blockchain and smart contracts, we use the following tools. The first one is Ethereum, which is the decentralized blockchain with smart contract functionality. Ether is the token for Ethereum blockchain. Solidity, which is an object-oriented programming language for writing smart contracts. Trueful is basically a framework that provides us and development environment for Ethereum-based smart contracts and testing. Ganache is a personal Ethereum blockchain to deploy and test smart contracts, applications, and run tests without any costs. Implementation. So user weights are stored in Solidity arrays. So the data structure we're using is arrays, and main functionalities in the smart contract are to store the weights in the arrays, aggregate the weights, and reset the weights. These weights, like I mentioned, are stored in the Solidity arrays. We have four main arrays in the contract to store the weights and the biases. All the numbers are multiplied by 10 raised to power 8. This is done because we cannot store float values in the smart contract, and we want to preserve the actual values as much as we can. So test users are the public keys that are provided by Ganache local blockchain. Implementation details for the hospital module. Hospital and the user modules are written using Python and PyTorch. Hospital deploys the smart contract. It also defines the initial random model for classifier, and it uploads these weights to the smart contract using the web3.py library. It calls the smart contract functions to aggregate the weights and also reset the matrices after every batch. Again, these functions are defined in the smart contract itself, but they're called by the hospital using web3.py library. Hospital also tests the performance of the final model in the smart contract using test data after every fork. Now, for the users are supposed to download the weights from the smart contract using web3.py library. They then divide these weights by 10 to the power 8 to counter the multiplication that we did earlier. They train the local model based on their local data, prepare the weights by multiplying by 10 to the power 8, and they also multiply it by number of samples, and then upload the number of samples as well as the weights to the smart contract. So here's the result and the discussion. So the pipeline updates the weights after 2 users, 4 users, or 8 users at a time. This way, the model can see more data. We experimented with total 16 online users. Random weights were initialized and uploaded by the hospital to the smart contract. And we used the BCE laws. So, like we mentioned earlier, the data sets are the PCAM and COVIDX. We also did a centralized training to compare our results, and we noticed that the closest result we get to the centralized training is when we have 2 users per batch for PCAM dataset. We assume that this happens because the rate of aggregation is more when we use 2 users in a batch for 16 users. Our future works include coding the user selection using weight norm and cosine similarity methodology. We are also looking into adding an incentivization mechanism for users in DeMed. Zero knowledge proofs to safeguard the weights. A more robust and scalable system can be built by using better infrastructure, better hardware, and also maybe in the future we can look into changing the data structures that we are currently using in the smart contract, and of course experimenting with more data sets. These are our references. Thank you very much.
And we welcome any question.
Okay,